we have worked some counting techniques. We might wonder, how do these counting techniques apply to other things beyond simply counting? Turns out in algebra, we have the existence of combinations through what we call the binomial coefficient. This evolves into what's called the binomial theorem. But let's start at the beginning, Pascal's triangle. So Pascal's triangle is this is actually a partial version of the triangle. This thing keeps on going. But named after the mathematician and physicist Blaise Pascal, the way this triangle works is at the very top we place a 1. That's what we call row 0, or n equals 0. In the row below that, we place 2 1s on either side of the first one. And it doesn't have to be this shape. These little shapes, these little polygons are really just kind of for visual aids, but usually you would not have it. You just have the numberings. So then the row below that, what we do is we always place a 1 on the left and a 1 on the far right. And then in the middle, you're always going to have the sum of the elements directly above it. So here, in this case, 1 plus 1 gives us 2. We have the 1 on the left and the 1 on the right. The row below that, we place a 1 on the far left, a 1 on the far right. Now we're going to have 2 sums. So these little shapes help illustrate this little indentation here. If you add up 1 plus 2, you get 3. And then you need another sum because there are 2 more adjacent elements. 2 and 1 give you 3. So again, the row below that, place 1s far left, far right. Now we'll have 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then our 1 there. And so on. This thing goes on indefinitely. So we have a series of rows here, so you can see how quickly this thing kind of blows up. Each row will have 1 element more than the row above it, but it progresses in this fashion. Now it turns out that if we look at something from algebra, what we call a binomial expansion, where we want to expand a binomial, binomial means 2 terms, x plus y, and we raise that to the 0 power, well, not surprisingly, we just get 1. Okay. Now, if we take x plus y to the first power, that's just x plus y. And I'm going to write that as 1x plus 1y. Now, if we do x plus y squared, we have to FOIL this. It's not just x squared plus y squared. It's x plus y times x plus y. And if you FOIL that out, you'll get 1x squared plus 2xy plus 1y squared. Okay, now I want you to start to notice that if you look at when you raise this to the 0 power, you get 1, which is the top row of Pascal's triangle. Okay, in the row below that, when our power is n equals 1, you get 1x plus 1y, which again, the coefficients are the binomial coefficients. In row 2, in other words, when your power is n equals 2, then you get 1x squared plus 2xy plus 1y squared. And let's see if we can infer from this, what would x plus y cubed look like? Well, it would be 1x squared. Now let me put a y to the 0, because technically there is a y to the 0 there. Y to the 0 is 1. And then we'll have plus 3x to the first, y to the first, plus 3x to the 0. No, I'm sorry, this should be x cubed. Let's rewrite this real quick. So we'll have 1x cubed y to the 0. If we do this, we basically have to do, first we'd have to distribute, in other words, FOIL x plus y times x plus y, which would give us this line, and then multiply all of that by x plus y, which would give us a lot of terms. 1x cubed plus 3x squared y to the first plus 3x to the first y squared plus 1x to the 0 y cubed. Now what I want you to notice is, again, if you were to do this by hand, you would get your coefficients 1, 3, 3, 1 are actually from Pascal's triangle. And the thing I want you to notice is look at the powers of x. The powers of x descend 3, 2, 1, 0. 3, 2, 1, 0, right? 3, 2, 1, 0. Powers of x go down in each term, and the powers of y, the way we've collected these, the powers of y increase. And that's how you could generalize this if you wanted to go to any power. For example, if you wanted to go to the 4th power, assuming that our pattern holds true, x plus y to the 4th, well, then your coefficients should be 1, 4, 6, 4, 1. And in terms of what these elements should be, it's going to be x to the 4th, y to the 0. Okay, so x will be the highest power, y will be the 0. Now step down your powers of x squared, x to the 1st, x to the 0, and step up your powers of y to the 0, y to the 1, y squared, y cubed, y to the 4th. And these are all terms of that expansion. So what we've just done, we've done a polynomial expansion, or since there's only two terms, these are binomial expansions. And the pattern that we notice here is that the coefficients of the terms in the expansion, as long as you descend the power of x, ascend the power of y, the coefficients of those terms are precisely the corresponding row in Pascal's triangle. Now, we're going to make a claim here. We're going to say the terms of that expansion, x plus y to the nth power, for n being any number 0, 1, 2, 3, etc., they have to be non-negative integers. So 0 is an integer, non-negative integer. So we claim that the coefficients for the terms can actually be read directly from row n of Pascal's triangle. Okay, so we saw that for a couple examples. That doesn't mean it's true. It just means we're observing a pattern. We're not going to prove that here. Additionally, we claim that for row n, the coefficients can be calculated by these combinations. So row n would be, and we might write this if you use the other notation for a combination. Remember, this means a combination where you have n things and you're picking 0 of them. Here you have n things and you're picking 1 of them, etc. And so actually, if you look at an example of this, if you look at row n equals 3, and you do n combination 0, well, that's asking, 3 combination 0, because n is 3 for this row. 3 combination 0 asks, if you have 3 things, how many ways are there to select 0 of them? Well, that might seem like it's 0, but it's actually one way. Yeah, you don't select anything at all. That is one way of selecting 0 things from 1, where order doesn't matter. And then selecting one thing, there's 3 ways to do that. The number of ways there is to select 2 things from 3 where order doesn't matter is 3, and 3 combination 3 gives us 1 as well. Well, fantastic. So that means that we have now generated the elements of row n equals 3, which if we look up here, check it out, we did good, 1, 3, 3, 1. Okay. Before I mention where this comes from, this is how you might see this stated. This is called the binomial theorem, that expansion, that our claim is called the binomial theorem, that if you want to take x plus y to the n, it's going to be the sum of n combination j, where j goes from 0 up to n. So that just means we're going across the row, right? 1, 3, 3, 1. This is n combination, 3 combination 0, 3 combination 1, 3 combination 2, 3 combination 3. And then x is, look at this, n minus j. So you're subtracting 1 as j steps up. So you have x to the n minus 1 until you get over here x to the 0. That'll be the last term. And y goes from y to the 0, y to the 1, y squared, etc., all the way y to the n. So here we have x to the 0. This is the way you might see it stated. And you don't really need to do that as long as you understand what we did up here. As long as this makes intuitive sense, then that's all that the binomial theorem is really stating. So why does this work? Real quick, let's think about it this way. This might be an unusual way to think about expanding things, but I'm going to have 4 terms generated here, right? Because everything in this parentheses is going to have to distribute to everything in the second set of parentheses. Even y is going to have to distribute, and this is where we get our first, outer, inner, last. But the way I want you to think about it is, how many ways are there for me to select 0 y's and 2 x's? Well, here I have 2 sets of parentheses. Okay, think about this in terms of n is the number of sets of parentheses that you have, because that's what the power tells you, right? So you have 1, 2 sets of parentheses. If I were to just randomly start this multiplication process, and I were just to pick an element in the first set of parentheses with which to multiply an element in the second set of parentheses, the question is, how many ways are there for me to select 0 y's and 2 x's? Well, to select 0 y's would mean that from 2 sets of parentheses, select no y's. Okay, well that automatically means you're selecting 2 x's, right? That means if you're selecting 0 y's, but you're selecting something from the parentheses, the elements that you are selecting have to be x's. But let's frame it as you're selecting 0 y's. So, order doesn't matter, right? Because we're ultimately, whether we pick y here and then y here, it's the same thing as if we pick the y here and then the y here. So from 2 sets of parentheses, select 0 y's. There's one way to do that. Now the next term will be select 1 y and 1 x. Well, again, the order doesn't matter. I could select the x here and then the y here, or the y here and then the x here. X times y is the same thing as y times x, so the order doesn't make a difference. And then same thing here. I can select an x from the first parenthesis and then pair that with this y here. Or I could select the y here and pair it with the x over here. So there's 2 ways for me to select 1x and 1y. Well, the combination answers that. We have 2 sets, select 1y. And we could answer that by saying from 2 parentheses, select 1y, and that answer is 2. So there is our coefficient for that middle term of Pascal's triangle. And finally, to select 2 x's, 2 y's and 0 x's, well, that means from 2 sets, select both y's, and 2 combination 2 gives me 1. We can go in the 3rd row and repeat this process, 4th row, repeat this process, the same type of thinking. The only difference is we'll have more parentheses, and we'll be drawing, say, from 3 parentheses, we want 2 y's and 1 x, which would be 3 combination 2. So there's a little bit of intuition for why this works. There's a cool connection, all kinds of cool connections between Pascal's triangle and the binomial theorem, but we'll leave it at that.